Hi, I'm Daisy and I'll be talking about matrix multiplication. It is one of the tools we learned from the earlier chapters in linear algebra. I find it interesting not only because of how applicable and useful it is as a computational procedure, but also because of its flexibility in the way it's used in proofs. The book provides 3 different ways to look at multiplications between matrices, and depending on the problems we're looking at, one way may be more useful for us than the others. We have 2 matrices A and B whose matrix product is defined. We can find AB by multiplying A with the columns of B. This captures the relations that the jth column of A times B is A times the jth column of B. When we need to prove that the product of 2 diagonal matrices is diagonal, this way of looking at matrix multiplication can be helpful. Since A and B are diagonal, their columns are multiple of the standard basis. And because A times the standard basis is the column of A times B is diagonal. The second way of looking at matrix multiplication is to multiply the rows of A with matrix B. If we have a system of linear equations with 3 variables x1, x2, and x3, we can view those 3 variables as the matrix B. Then the 3 equations given to us are the 3 rows of A. This makes each values on the right hand side the product of a row of A times B. This way of seeing matrix multiplication allows us to go back and forth between linear systems and matrices. This is the idea behind section 3.4, for if we have equations with a bunch of x values and y values, we can find the lines of best fit that goes through those data by viewing each equations as a row of A times B and solving for B. The last way to do matrix multiplication that the book shows us is to multiply the rows of A with the columns of B. Each operation will give us an entry of A times B. In problem 2.3.12, we are asked to show that the product of 2 upper triangular matrices is an upper triangular matrix, and the same thing for lower triangular matrix. Because the definition of an upper triangular matrix provides the conditions on I and J, we should use this formula to look at each individual entries instead of looking at the whole rows or columns of the products A and B. One common trick from matrix multiplication that appears in proofs is pulling out columns of a matrix. For example, we pull out the jth column of A by multiplying A with the standard basis E sub j. We can also think of V, an n by 1 matrix, in 2 different forms, one of which is the matrix product of the n by n identity matrix with itself, and the second way is to add up all the products of each entry of V with the standard basis vector corresponding to that entry. The way linear combination is defined also involves matrix multiplication. Let B be the linear combinations of a list of n vectors that are the basis of Fn. Then by definition, B is the sums of multiples of V1 to Vn. Problem 3.2.19 asks us if we can recognize that B can also be written as the product of a matrix V whose columns are the basis and the vectors of all the coefficients A1 to An. Matrix multiplications also represents linear transformations of linear maps. We generate different geometric transformation by multiplying matrices together. For example, we know that the matrix of the linear map R theta is this matrix A, and the matrix of the linear map T that reflects across the y-axis is this matrix B. So we can find the matrix of a linear map that rotates counterclockwise by theta and then reflects across the y-axis by multiplying B by A. Matrix multiplication is relevant in lots of concepts such as linear system, eigenvectors, eigenvalues, standard basis, linear combinations, and transformations. Although having three ways of looking at matrix multiplications can be a challenge in the sense that it's not obvious which way we should go with when we encounter a problem. It gives us space and tools to work with a variety of problems.